Hello everyone, I'm Chris McIntosh. I help teach the statistics courses. We're going to go over your Week 10 computer assignment. The objectives for this week are to conduct a one-way ANOVA in Jamovi, interpret the results for a one-way ANOVA, report the results for a one-way ANOVA, and interpret a base factor for a one-way ANOVA. We're going to open the data set in Jamovi. So go ahead and open up Jamovi. And last week we installed the LSJ data module. If you didn't install it or you still need to, you can go to the modules, library, and search for LSJ. And you want to click install. I already have it installed. We're going to open, oh, I didn't fix that text. We're going to open a clinical trial data set. So let me fix the text really quick on my slide. Okay, so go to the hamburger menu, open, data library, and we're looking for one that says clinical trial. Oh, it's up here towards the top. And want to add your name to the top of the results. Let's go ahead and go to analysis, exploration, descriptives, and on the results, add your name right before the word results. You want to use the statistical analysis checklist for week 10 for the one-way ANOVA. And that will have updated information for this week's material. And we're going to answer the questions in section 1, the study information. The study purpose, again, this is a learning exercise. The data are fabricated and results are not generalizable, but if you're doing this for your own analysis or critiquing a study, you'd want to just describe what the purpose was. The research question, Navarro did provide a description of this example, and the gist of it was participants are randomly assigned to one of 3 groups: placebo control group, existing medication, axi-free group, or new drug joyzepam group. And then the question was, is mood elevated after a 3-month period taking the drug? And it was hypothesized that the new drug will show the largest improvement. Study design, they described a little bit of this study design. They said it was a double-blind random assignment with a control group, and there's manipulation of an ID. So this is an experimental design. Ethical considerations, nothing was described. Data collection and handling, nothing was described. You want to answer the questions in section number 2, the data set information questions. The variables and level of measurement in the data set. We can click on the data tab, and we have an ID variable, and that looks like it's nominal. We can double check that it's set up as nominal. We have a drug group with 3 groups, a drug variable with 3 groups. That's also nominal. We have a therapy variable with 2 groups, and that was also nominal. And we have a mood gain variable, and we would call that continuous in Jamovi, and this was a psychologist assessing mood gain, and I would call that interval level of measurement. It's not a physical measurement that we can take, so this is kind of a psychometric type of thing, and I would go ahead and call that interval. Data accuracy, we can kind of get an idea by looking at descriptive statistics. And when you have categorical and continuous variables mixed together, you want to get those descriptives separately because you want to look at some different descriptive statistics. So let's do the categorical variables first. I'm not interested in ID, so we're not going to do that, but we can drag drug and therapy over to the variables box, get frequency tables. In the statistics, we do not need the mean and the median of categorical variables, also standard deviation, minimum, maximum, so we can uncheck all of those. And we can leave the N and the missing because that's useful. We can see we have 18 entries in drug and 18 entries in therapy, and no missing variables, no missing data in either of those. And then we have frequencies for drug. We have 3 groups: anxiety-free, joyzepam, and placebo, with 6 in each one. And therapy, CBT, and no therapy, with 9 in each one. And let's go ahead and get some plots, and we would get bar plots for those. And not surprisingly, they're very equally distributed. Okay, let's get descriptive statistics for the continuous variable. So we're going to go to Analysis, Exploration, and Descriptives again. And you see it gives us a new set of output, and we're going to do mood gain as our variable. And we know that this is looking at 3 groups split up by drug. So let's go ahead and split this by drug. And we're getting mean and standard deviation, which is going to be over here. And we can go ahead and get some plots. And this is continuous variable, so we'll do histogram, box plot, and we know we're going to look at normality, so we can do a QQ plot there. So means, so we see anxiety-free, the mean is 0.717, joyzepam, the mean is 1.48, and placebo, the mean is 0.45. So we can see one group is higher than the others. Standard deviations, 0.392, 0.2, 0.28. So pretty close together. The anxiety-free had a little wider standard deviation than the others, but not crazy big. We'll see how that looks when we get to things. The histogram is split out by the 3 groups, and it's going to be easy to see that joyzepam is the highest, anxiety-free is in the middle with a good bit of overlap with the placebo, and then the placebo down here close to the bottom. And box plots also show that same relationships with each other. So it's a good idea to get kind of an idea of what the story might be with your descriptives before you even do a test. So we ought to be finding joyzepam as the highest, anxiety-free is the second, and placebo. And then the real question we're going to answer is, are they different enough to be statistically significant in the differences? So that's going to be the question to answer. And with our QQ plot, it's split it up into groups too, and each one looks fairly close to normally distributed. So that looks pretty good. And data accuracy, I don't see any spelling errors. All the values look pretty reasonable. Data manipulation, I keep forgetting to update the text, and there is nothing that we need to do to change the data in this data set, so we'll change that to none. Okay, we'll move to section 3, the test information. and this is for a one-way ANOVA. So test selection, if we looked at our table that we've been building for which statistical test, one independent variable, one dependent variable, and our dependent variable is going to be the outcome variable, which is continuous, so it's going to be down here in interval and ratio, and our independent variable is nominal. So we've added in down here 3 or more groups, a one-way ANOVA. If we have skewed data or not normally distributed data, then it's a Kruskal-Wallis test. And that's the same for if we have a nominal or an ordinal independent variable. And so you'll see those tests are repeated right there. But if we were doing this with StatCat, we can go into StatCat and hit group comparison. So it's that second option again, like the t-test, we're doing group comparisons. And our dependent variable is our mood gain, our continuous variable, and our independent variable is our categorical variable drug with 3 groups. And StatCat recognized that this was had 3 groups, more than 2, and suggested a one-way ANOVA. And if we had normality assumption violated, then we could do a Kruskal-Wallis test. Okay, our independent and our dependent variables, we looked at those. The dependent variable was mood gain and independent variable was drug, and we talked about the level of measurement, interval, and nominal on that. Test assumptions. So our sample is randomly selected from the population. Didn't really go into a sampling plan in this description, so we won't, but you would know that from the study design if it were described. Observations are independent. Yes, we know that from the study design, that these are different individuals assigned to different groups, randomly to different groups. Data are normally distributed. We can go ahead and look at that assumption and homogeneity variance. So let's go ahead and get into the analysis, ANOVA, and ANOVA. There is a one-way ANOVA menu, but it has a fewer options. And we're going to go ahead and skip that one and go to the ANOVA menu. And our dependent variable is our mood gain. And our fixed factor is our drug. And this is a place where terms for different tests, sometimes there's more than one term, and we have been calling it an independent variable. And in a lot of research, a variable that divides participants into groups is often called a factor. So drug is our factor, or our independent variable, our categorical independent variable. And we want to go down to assumption checks, and which is the second menu down, and click on homogeneity test, normality test, and QQ plot. So if we look at our homogeneity variance test, and that's Levine's, this is the same Levine's test that is used in with t-tests, so it doesn't matter if it's 2 groups or more than 2 groups. And we can see that we have an F statistic of 1.45. That's fairly low for an F statistic, and a p-value of 0.266, which is not significant. So we do not violate our homogeneity variance assumption because we're not significantly different from homogeneous variances. So that's good. In our normality test, our Shapiro-Wilk test, the p is 0.605, which is also high, so we do not violate our normality assumption. And if we look at that QQ plot, we can see the data run pretty close to the normal line there. Okay, so that's good. We passed all of our assumption tests. Now we can follow our null hypothesis significance testing steps. Our null hypothesis is there is no difference between the groups. And if you went through the readings, you would notice that if it's 3 or more groups, it's any difference anywhere. It doesn't have to be between any particular one. It doesn't have to be between all of them. So you could have 3 the same and 1 different. That would still be a significant result. The alternative hypothesis, or H1, there is a difference between the group means. Step 2 for NHST steps, our criteria of rejection is alpha 0.05. Our test statistic here is an ANOVA, and then we're going to go look at our results. So if we go back up here to our ANOVA, we see we have this test here, and we're going to add a couple things in. We want to see some effect sizes. I was taught using a partial eta squared, and Navarro describes another effect size called an omega squared. So we'll go ahead and get both of those. We'll see they're pretty close to each other. I was also taught to really not use an eta squared. And as Navarro noted, that can be a little bit biased, so it's generally not recommended. So what I've seen published is a partial eta squared typically. The model, I think that's set up automatically, so we don't need to change anything. We have our assumption checks, and we're going to do post hoc tests. So this is the first place that we're actually going to see an official post hoc test. So we can pick a drug and move it over. You can either click it and push the arrow or just drag it over. And you have some choices here on post hoc tests. And your Heavy book has not emphasized this a lot, but the more statistical tests that you run, the greater your chance for a type 1 error. So if on a particular test we use alpha 0.05 as our accepted error type 1 error rate, if we conduct one test, then that's what we can use as alpha equal 0.05. When you start conducting multiple statistical tests on a data set, then you run that risk of having a type 1 error with each separate test. So if you're using 0.05 on every test, your study-wise error rate actually goes up. And there's a specific formula. It's not straight up additive, like not adding 0.05 every time, but we're not going to get into the formula, but just be aware that the more tests you conduct, the higher your type 1 error rate goes. And when we know we have a significant ANOVA result, that tells us there is a difference somewhere, but we want to see where the difference actually lies. And so that's why they do these post hoc tests. And there are some choices in the types of post hoc tests that you can conduct. And no correction, meaning you're not really correcting anything specifically. Tukey is one that I learned in school. It's a pretty middle of the road test. It does a correction, but it's not really strict. The strictest one that I'm aware of is Bonferroni, and basically that takes the number of tests conducted. It takes the alpha level and divides by the number of tests conducted. So if you use alpha 0.05 as your starting point and you conduct 3 tests, then you take 0.05 divided by 3, and that's like 0.0166 or something like that. But basically you divide your alpha level by the number of tests you plan to conduct, and then you use that new significance level, that new alpha level, as your level to decide if something is significant. I'm just going to leave it at Tukey. That's a pretty middle of the road option, um, and we'll just go with that. And we don't need to worry about these other menu items, estimated marginal means, or save. So let's go through and look at these results. So we get this ANOVA table, and we have drug, that is our independent variable, and then we have this line that says residuals. And we get these values here, Heavey and Navarro go into some depth about how these sum of squares and degrees of freedom and mean square and F are calculated, but we're not going to jump into a lot of depth in this course. The PhD students, they get to jump into a lot more depth on that. So count your blessings for this. But and you get the category of sum of squares between and sum of squares within. And I added the part of our checklist talking about tests, and we added this line. So we're going to report both of those to the reader, degrees of freedom between and degrees of freedom within. Degrees of freedom between is based on the number of groups, and within is based on within a particular group. So if we look at that, the drug is our number of groups, and its number of groups -1, I believe, so 3 minus 1 is 2, and then here's our within is 15. So then we're going to look at our F value, which for this table is 18.6. That's quite a bit higher. And then our P value, and it's pretty low. It's just going to give us less than 0.001. And our partial eta squared is 0.713. Our omega squared is 0.662. They're both pretty high. And I did add just some guidelines here on the checklist. For a partial eta squared, 0.01 is a small effect size, 0.06 is medium, and 0.14 is large. As you can tell, these are quite a bit smaller than what we saw with Cohen's D. And omega squared, I looked that up, and I had 0.06 is small, 0.14 is medium, and greater than 0.14 is large. And you know, they're all a little bit arbitrary, and there's some loose guidelines for everyone, and every effect size is a little different. So honestly, when you find an effect size that you don't know, and I still run into them here and there, I just Google it and then Google how's that typically interpreted. So, but 0.14 is large, and we're well above that, so we have some very large effect sizes here. And we know it's a significant result. So the question then becomes, where do the differences lie? And we already had an idea that our joyzepam was higher than the others, and then Angzifree was in the middle, and placebo is at the bottom. And so here's our post hoc comparison table. So we know we had 3 groups, and this can look like a lot of lines, but in reality, we're just finding the combinations of the 3 groups. And so here it started with Angzifree and comparing that to joyzepam, and Angzifree comparing that to placebo. So if we look at our T and our P value, we see that the T is -0.4 or 4.36, and again, this joyzepam is going to be the highest, and so this subtract that is going to be a negative number, but the magnitude is definitely big, and that P is 0.002, so that is a significant difference between joyzepam and Angzifree. And Angzifree with placebo, if we look, we see the T is 1.52. That's not very high, and the P value is 0.312. So the differences between anxiety-free and placebo are not statistically significant. And then there's one more combination that we didn't look at yet, and that would be between joyzepam and placebo. And very conveniently, the next line is that last combination. And it gives us that. The t is 5.88, which is even bigger than the other one. The p-value is less than 0.001, so joyzepam is definitely statistically significantly different than placebo. And we'd already looked at the descriptive statistics, but to know what's bigger than the other, you can, try and think it out in your head using these signs, but it's very convenient to, did I get, descriptive statistics? Well, I guess it didn't give me an option for descriptive statistics on here. So definitely you want to run those descriptive statistics, because this was not like a t-test where we had the option to get them again. So yeah, we would go look at our descriptive statistics that we looked at the beginning and describe where our differences lied for that. So that is kind of an overview of those results for a one-way ANOVA. And this is where the model's a little more complex. We have 3 groups, and as you can see, there's a little more involved in running this test and interpreting the results. Our partial eta squared we said was very large. So you'll notice that there was no Bayes factor on this test, but we can actually import a module to let us get a Bayes factor for an ANOVA test. So we're going to go ahead and do that. So if you go to Modules, Jamovi Library, and we're looking for this JSQ module, you can search for that. It should come up, and you want to install it. I already have it installed. And once you install that, when you go back to your analyses, if we go to Analyses and ANOVA, you'll notice that there's a new menu down here at the bottom, and we have some extra options. And we're going to select this Bayesian ANOVA. And there's a number of things that we get, but we're really just interested in this Bayes factor right here. And so we're going to take mood gain and drag that over to dependent variable, and we're going to take drug and drag that over to fixed factor. And you'll notice that we can actually switch between a Bayes factor 1,0, which is what's the evidence supporting the alternative hypothesis, and a Bayes factor 0,1. They're just the inverse of each other. It's a fraction, and it's just putting one on top of the other or swapping it. And if we get that, we have our Bayesian ANOVA, and for our model including the drugs, we have a Bayes factor 1,0 of 245.9. You can see this. It's really easy to, if we switch that to the Bayes factor, what's the evidence supporting the null hypothesis, you can see that we have this small fraction here. So definitely, I liked Navarro's convention of reporting the Bayes factor as a whole number and just switching which form you see it in, and that tells us. And we remember from our reading that much above like 120 was very strong evidence. So this is strong evidence in support of the alternative hypothesis. So that is good to understand. So again, what's the story the data are telling us? And we want to tie these results back to our original story. And I didn't update that text either. And so let's go ahead and update that on the fly. The So the joyzepam showed a greater mood elevation than the existing medication and the placebo. So we'd done a good job of talking about that. And report results. So let's try this out for the ANOVA. It's done pretty well. ChatGPT's done pretty well for results for our tests up to now. So let's go ahead and open up ChatGPT. And we can paste our prompt in. Please report the results of a one-way ANOVA. Include some of these results and an interpretation. So I'm going to paste in my prompt, hit Shift Enter to go down to the next line. I'm going to get into Jamovi and let's give it I think that was my other copy. Okay, so let's give it some descriptive statistics first, and I'm just going to clean this up just a little bit to give it this, and let's get rid of the min and the max and the median, and that gives us our mean and standard deviation. So I'm going to right click on that and hit copy, and then go to ChatGPT and Control V to paste and Shift Enter to go down to the next line. And then let's go to our ANOVA table, which is right there. Right click on it, go copy, go to ChatGPT, Shift V to paste, Shift Enter to go to the next line. Let's give it our assumption checks, copy, Control V to paste, Shift Enter to go to the next line. Our normality test, copy, whoops, Control V to paste, Shift Enter to go down to the next line, and let's give it our post hoc test to copy, Control V to paste, Shift Enter, and I'm just going to type in the Bayes factor, which we said was 245.9, and hit Enter. Okay, one-way ANOVA was conducted to compare the effect of drug type on mood gain. Descriptive statistics for each drug are as follows. Anxiety-free mean 0.717 with a standard deviation. Joyzepam mean 1.48 with a standard deviation. Placebo mean of 0.45 with a standard deviation. One-way analysis of variance was conducted to determine whether there was significant differences in mood gain across the three drug groups, anxiety-free, joyzepam, and placebo. The null hypothesis, there was no difference in mood gain across the drug conditions. The alternative hypothesis, at least one drug condition differed in mood gain. The results of the ANOVA revealed the significant effect of drug type on mood gain. F2, 15, which are degrees of freedom, between and within equals 18.6, p less than 0.001, indicating that at least one group mean is significantly different from the others. The effect size partial eta squared was 0.713, suggesting that approximately 71% of the variance in mood gain can be explained by drug type. The omega squared was 0.662, which further supports a strong effect of the drug treatment. Homogeneity variance The assumption was met. Normality, suggesting the results were approximately normally distributed. Post hoc comparisons. Tukey's post hoc test was conducted to examine pairwise differences between the groups, and it went through and compared each one and identified the significant differences. And not significant differences. Interpretation and conclusion. The results indicate that joyzepam led to a significantly greater mood improvement compared to both anxiety-free and placebo. While the difference between anxiety-free and placebo was not significant, the effect size suggests a strong influence of drug type on mood gain, and assumptions for ANOVA were met. Thus, joyzepam appears to be the most effective drug for mood improvement, whereas anxiety-free does not provide a significant advantage over the placebo. So again, that is a pretty good write-up from those results, and this will certainly help you interpret your output. So I am pretty pleased with that write-up from pasting some results. And you want to click down at the bottom of your output and make sure your cursor is blinking. We copied it from ChatGPT and we're going to paste it right there so that we can save our results with our output, or save our write-up with our output. And let's double check that we don't have anything else. Save your Jamovi file. So hamburger menu, save as, navigate to your folder, make sure you save this with all of your output. Let's go ahead and, well, actually I'll go ahead and save it. I don't think I've saved a copy of this yet. Might be helpful for later. And then save a PDF of your results. So we're going to go to hamburger menu, export, make sure that we are in the correct folder, and just make sure that's a PDF output. Okay. And then answer the computer assignment questions and submit your PDF output in Canvas. That is all for a one-way ANOVA, and I hope that is helpful in understanding that test a little bit more and how to run it and interpret it. We'll talk to you later.